What? You need to turn all the way around.
All right, guys.
Okay. Oh, I better turn this off. This is the reading quiz, Rahi. And I just we've got a few others. We have.
We're just gonna talk to Rahi right now.
We're just. No, I'm not
I
gonna
could
do
just
that.
imagine some random person watching this video.
I don't think any random person's gonna watch this video.
No, what?
We only have a few minutes left, really. We've done the integrated rate law, and I'd like to at least introduce you to what the differential rate law looks like. It's two different kinds of rate law. They both look very different, and it almost appears that they just give totally different things because they look so different, but they give you the exact same information. Depending on the order, we have three different equations for the integrated rate law. I remind you that the slope is negative for these two, but it's positive for this one. We talked about that yesterday. Do you remember why the slope is positive here but negative up there?
Because it's inverse.
Yes. During the reaction, the concentration of the reactants goes down. So this number would be going down during the reaction, so we have, when we have the concentration on the y-axis, it's falling. Same thing here. As the concentration falls, the natural log of the concentration falls. So that would be falling as well. But as the concentration falls, its inverse increases. So you get a positive slope on that one. So when I ask for an integrated rate law, it should look like one of these equations, depending on what the order is. And you find the order by which one gives the straight line. For integrated rate law, you're going to use concentration versus time data. That's how you know you're going to have an integrated rate law. Concentration versus time. If you're given concentration versus rate data, then there's no rate term in here, and you can't do much with that. You have to use the differential rate law for that. And that's what we'll start with today. So I want you to know that we're going to start looking at differential rate law today. We're not going to get very far. But tomorrow in the lab, it's all integrated rate law. Okay, so the differential rate law, no matter what order it is, it's going to have this form. I will tell you that the differential rate law is pretty easy. It's not difficult at all. The problems are longer, they're presented longer, but the way that you use the data is very simple. So a differential rate law is going to look like this. Rate equals the rate constant times the concentration of the reactant to some power. Now you've seen this already. I was deriving those integrated rate laws with this, right? This would be concentration versus rate. Okay. So just defining what these terms are, and I know that we've been through this already. Now, the K is the rate constant. The power n there is the order of the reactant. I mentioned this yesterday, and I want to just toss it again, because the more that you gather about this in your brain process, I think it's good to hear this a couple of times. The order. Order doesn't really mean anything to us yet, but what it does is it tells how the concentration of the reactant affects the rate. That's what the order is. If you have a zero order reaction, that means that you can do anything you want to the concentration of A. As long as there's some A there, the rate's going to be constant. That means A's concentration is not going to affect the rate. You could double A or increase it by 10 times. The rate's going to be the same no matter what. If the reaction is first order, That means that if you double the concentration of A, the rate is going to double as well. Whatever change you apply to the concentration, the same change applies to the rate. If you increase the concentration by 10, the reaction is going to go 10 times faster. That's what that means. If you cut it in half, the rate gets cut in half. Now, if it's second order, if you double the rate, if you double the concentration, the rate is going to change by that change squared. That's what second order means. So if I double this concentration, then the rate is going to go up by 4, 2 squared. If I increase the concentration by 10, what's going to happen to the rate? It goes up by 100, 10 squared. What happens to the rate if I cut the concentration to 1/3 of what it was before? It'll be, no, not the third root, it'll be 1/9, 1 over 3 squared. So second order means that whatever change that I apply to the reactant concentration, the rate is going to change by that first change squared. All right, so that's what the order means, and we'll be going through that again and again. I just want to try to make that clear. So when you're given concentration versus rate data, this is how we find now the order of the reactants that are in the reaction. You have to run the experiment several times, several trials, and then just see how the concentration affects the rate. If you double the concentration of A and nothing happens to the rate, that means it was zero order. And so on. Your arms aren't getting tight, are they, Cam? Yes?
Are we going to be learning anything more than differential rate laws and integration rate laws?
Oh yeah, you mean, what do you mean anything more than? Yeah, there's other topics in the chapter. We're talking about rate right now. We also have to talk about mechanism and collision theory.
If you were to give us a question on the test about this law, what would it be?
I'd give you several trials of an experiment, tell you what the chemical equation is, and I'd say determine the rate law. And you'd come up with something that looks like this with a number up there for it's either zero first or second order.
And then we would have to plot every point to see.
You don't have to do any plotting when you do the differential rate law. No, it takes less work to find the differential rate law. Everybody good with this slide? And I have one other slide for you, then we just talk about the units on K and we'll quit. So, I just want to mention the value of K there. I mentioned yesterday that K tells us how fast the reaction is. If you have a high K value, that means the reaction's fast. If you have a low K value, the reaction's a slow reaction. So, the way we find the K value is, and don't rewrite all this because this is the same as the top of the other slide. When you have a set of concentration versus rate data, find the order. So you're going to know what the exponent is there. And then just choose any one of the trials and plug in the rate for that trial and the concentration. And the only thing you won't know then is the K value and you solve for it. It's extremely easy to find K. Yes, Empress.
So then when you're solving for k, would it be like a to the power of x? Or?
Yes. Yep. If it's second order, for instance, it'll be whatever the concentration for that trial is squared. Yeah.
So now what do you think when doubling 8 into nothing to the rate, which of multiply by k and then find the
Yeah, but k is a constant.
right? But then that would change the doubling it.
Well, if you double something to the 0 power, what does that cause it to do?
Like for example, if it was the second power. Like
Oh, if it's the second power, then if you double it, this now would be 2a, and it would be squared. So that's why the rate would go up 4 times.
if you change the k, it wouldn't double or triple, it would be a completely different.
You need to assume that k is not changing. Now, you can change k. If you increase the temperature, the k is going to go up. But you're assuming that throughout several trials of the same experiment, you're assuming that k is constant. Okay, even if you change the concentration, the k is not changing.
Right, I mean, like how would we find the order if you don't know what k is?
From this,
Right, but if you double a and k is something other than 1, then it wouldn't double, it would like,
yeah, it would, because k is the same.
the rate would double.
Yeah, that's what it says.
I'll ask you.
Okay. I'm leaving with 1 minute before the end of class.
Alright.
I'm just kidding with you. All right, so let's talk about the units on k. Now, can you see how if the order changes, the unit on k might change? It would.
Yeah.
It would change. Let's take a look at this. First of all, I'll come over here. What would be the unit on rate? What's this unit right here? Rate. How do we measure the rate of a reaction? Rate is always something happening over time. What is changing when we look at the rate of a reaction?
Concentration.
The concentration, that's right. So the unit for rate is molarity per second. Would you buy that? How fast is the concentration changing? Okay. So if we have a 0 order, or a first order, I'll just do 0 first and second. Now the rate equals k times a to the 0 power. This rate is k times a to the first power. And this one let's talk units. The rate is always molarity per second. If you have, now we want to know what the K is, so I'm just going to put K there. A is always a molarity, it's a concentration. Molarity to the 0 power would give you what unit? The number 1, you don't have a unit on it. It just, anything to the 0 power is just 1. So the unit just goes away when it's 0 order, it's a unit of this thing. So the K value for 0 order is just molarity per second. Because rate equals K, essentially, for 0 order. It doesn't affect, or it's not affected by the A value. Now what about for this one? We have meters. Molarity per second equals K. What would be molarity to the first power? That's just molarity, right.
KM.
Oh yeah, KM. This is for you. Okay, now, if I want to solve for K, we're trying to solve for what is the unit on K, so get K by itself. It would be 1 over second. So if it's first order, the unit on K is 1 over seconds. And I will tell you, by the way, when you use the integrated rate law, these units on K apply to those too. The 0 order K would be molarity per second. First order would be 1 over second, like that, and so on.